Okay, good morning everyone. I think for today's class, we're going just to continue a little bit chapter 14. And for next Monday class, if there are no announcement in Moodle from me, it means you don't need to come to class. Okay. Yeah. Okay, so I think we can, so yesterday we start from limit and continuity in the function of two variables, and we can see that because when we approach a point in three-dimensional system, especially in the xy plane, we are having some infinite ways to get close to that point, okay? And then we can approach the point based on the curve that we can create. For example, we can create the curve that is along the x-axis or y-axis or y equal x, okay, to get close to the point that we want to approach, okay. And we can take the limit and then check whether it is equal or not. If it's not equal, that means the limit of the function of two variables, it doesn't exist, okay. So it's going to be this one. Okay, now after the limit, we're going to see that the continuity. Okay, so we can see that it's the same with the calculus 1. So the limit should be equal with the value at that functions, okay? For example, if we have a functions, for example, a function that is a function of xy, like this, and we say that if we look on the denominator at this part here, of course we would like to have this not equal to 0, right? So f is discontinuous at 0, 0, right? So we can set some domain for this one. Domain is xy as xy is not equal to 0, 0, which means aside from 0, 0, the function will be continuous. Okay, that's just one example. And I think the same thing with the three variables. I think I would just skip that. That's basically the same. You could just add z. So for example, continuity for three variable z is going a, b, c, and this will be x, y, z. And this is going to be equal to the f, a, b, c. So the same thing. Okay, we just add another variable. Okay, next is what we call technically the partial derivative. Okay, partial derivative, which is the core of this chapter. So if f is a function of two variable x and y, suppose x is vary, which means we can set x as a variable that is going to change, and then keep y fixed. Let's say maybe y equals some constant b, like that, and b is a constant. So we consider there is another function, let's say g of x, that is a function of x and b, the constant b. If this function has derivative, if g has derivative at a, then we call this partial derivative of f with respect to x at a, or at a b. Okay. Or we write like f and then having subscript x, like that, and then ab. So we call this as a partial derivative of f with respect to x at ab. Or we can rewrite this partial is equal to g prime a, where g of x is a function x and a constant b, with a constant b. Okay. So we start from f is function to variable x, y, okay, and then x we make it vary, and let's say the y is fixed as a constant b, and we develop another function we call g. So g is actually a function of f, but the y is constant b, okay, and if g can be derived, becomes g prime. It means that this g prime is actually partial derivative of f with respect to x at ab. Okay. And by definition, this g prime we can write in terms of limit, if you remember. So this is g a plus h minus g of a divided by h. So the equation becomes the whole partial of x at ab. This will be limit you will notice that the one we are going to change is only the x. Okay. Now the same thing, we would like to take the x as a constant and y will be the one that will be varied. We are going to have a partial y, a partial derivative of y. So you can write here, let me write first in this case. So we can also have this of y now the x as a constant, and then we see that the y will be having a changing some distance h. So we say that this is a partial derivative of f with respect to y at AB. And now we can have general definition for both partial x and partial y as this. Another way to write the partial, we can have some options, some notations that can, they are all the same meaning. So we can write like f with subscript x, f subscript y. We say that this is partial derivative of x, partial derivative of y. We can write with this Leibniz notation, dou f dou x, or just simply d d1 or dx. You can also write f1 like that. They are all the same thing. Okay? Regardless of which one you pick as your partial derivative notations, it doesn't really matter. Okay? They are the same. They are the same. So you could just pick which one you prefer. Okay, and then we can see how, in practice, how we can use this partial derivative. So whenever you have a function of more than one variable, we can take this approach. Okay, so procedure. So example. So if take, let's say we have a function 3x minus x squared y squared plus 2x cubed y. Now if we want to find the partial of x, then we are going to derive this expression. So first we want to take x normally, because this is partial x, and then for y we are going to treat y as a fixed constant, okay? Just like in our definition in the middle. Okay? So we take this derivative as usual. So 3x become 3, x squared become negative 2x, so negative x squared become negative 2x, and y squared is just a constant. And then the same thing on the right side, this will be 6 x squared and then y. So let me write here, we treat y as a constant. And then if we have partial y. Now we are going to treat x as a constant. So treat x as a constant. Treat. Which means x becomes 0 when we derive because it's a constant. So 0. And then y squared becomes 2y. So negative 2. And then x squared y. And then plus 2x cubed because y becomes just a 1. Okay. If you're not really familiar how to take the partial derivative, my suggestion is whenever you partially derive, for example, partially derive x, you can just think y squared maybe just a number, maybe a. And then we can think a as a constant. So you can actually ignore this y and then just write that as it is. Same thing if we derive with respect to y, then we can think x as a number or as a constant. Okay, another example. We have fxy. Okay, we have that. So question is evaluate a partial x, partial y at 1, ln 2. Okay, so we can start, take partial x. So we are going to have two components, this for x and e to the x squared y, right? So we need to have a product rule for this x. Okay. So the first one will be e x squared y. And then plus, we derive the e with power of x squared y. This will be 2 x squared y, and then e x squared y. Okay, let me maybe make it more clear. So this is f g. Remember that when we have f g, this will be f prime g plus g prime f. Okay, and let me write here the f prime is just 1, g prime is maybe this is going to be confusing. Maybe let me write but do you get it? Do you get it, this partial x? Okay, any questions? Or still confusing? Why this is the answer? Okay. So first, we are going to have these two components, which is going to be the product rule. So the first one is the f prime g. So f prime becomes just 1, and then this is the result. The second one is g prime f. So we are going to have f, okay, f. So that will be x. So maybe let me write here, just maybe to get into. So this will be x, and then g prime. So g prime for e with power of any number, it will be that original one. So we write all the things, and then we chain rule with the x squared y. But we are only taking derivative of x. So x squared becomes 2x. Y is just as it is 2xy. 2xy multiplied with x, 2x squared y, e. Okay? Clear? So this is going to be 2xy and then e. And that's it. Okay. And then we are going to plug in the number 1 and ln2, because that's the one that the question asks. Okay, we plug in x equal 1 and y is ln2. So this will be e ln2 plus two ln2 e ln2, or this will be e ln2 is 2, okay, plus this is another 2, so this will be 4 ln2, okay. Now the partial y. Now for partial y, we can ignore the x, so we can just focus on the right one that has y. So this partially derived, e is still e, with chain rule of the x squared. Okay? So we can have x cubed and then e with power of x squared y. And then taking that into a 0.1 ln2, this will be e and then ln2 or 2. So this is the answer. Okay, maybe one more example. Okay. Let's say we have f is sine x over 1 plus y. Find the partial x and partial y. So basically, we have this. You can use chain rule. So every time we have the sign, another function inside, we take the outside function, derive, So both partial y, partial x should be start from cosine at the beginning. Okay, cosine, something inside, multiply that the one inside. Okay? We derive the chain rule. Okay, partial x is cosine. Put everything inside. I think I will write all the steps, and then we multiply with the derivative, partial derived with respect to x of x over 1 plus y, which gives you is cosine x 1 plus y, and derivative of x is just 1, so this will be just 1 over 1 plus y, and that's it. A partial y, same, we write cosine like that, multiply with the chain rule for the partial y. So derivative with respect to y, this will be x. So you can think x as a constant, right? So we need to derive 1 over 1 plus y. Okay. 1 over 1 plus y, you can just imagine like 1 over x. 1 over x derived, it will be negative 1 over x squared, right? Or you could see from the x with power negative 1. From here, if we derive this will be like that, right? So this will be, so the same thing, we have 1 plus y minus 1, so it will be minus 2. So we can have, but we have negative 1 over 1 plus y squared multiplied with x. So this will be, because x is just a constant, so we are going to have, this will be, let me write negative in the front. Okay, negative cosine. Negative is from the chain rule. So this will be x over. Okay. It's negative is from here. It's negative from this one. So I put negative here, and then this will be this. Okay. Now, interpretations of our partial derivative. Let me write here. Geometric. So the geometric interpretations. So let's say we have this S, the surface S, and let's say we are going to, let's say, pinpoint a point P, this one here. Let's say this P is at the A, B, C. Okay? And notice that at that point, we can have some line. We call this is T1 and T2. It's stated from the tangent. So T1 is the tangent. Okay, that is actually on the same par with the x-axis. The t2 is the same par with the y-axis. Or we could see the s, and then we see the curve c1 and c2 that is making the cross sections, okay, in the point P. So let me write what is the interpretation here. So recall, let me write. So recall that we can write z as a function of xy, okay, that representing surface S. Okay, the point P is on the surface, is on the surface S. Okay, and then if we restrict y equal a constant b, like we did in the techniques, okay, we make y as a constant, then as a consequences we restrict observation only to C1, okay? And if we set not y, sorry, x as a constant, then we restrict observation only to C2. So this C2 is when x equal with a, which means here. So we are just seeing the curve. And the C1 is when we set equal b. So y equal b. Maybe let me write here a and b to make it clear. So a is on this one, b is on this one. Okay. So x equal a is this, y equal b is this. Okay. So the C1 and C2, they are parallel when you see on the top. Okay, so they are on the same line with the x equal a or y equal b. Okay, for that one. Okay, you see, you can take this and see that, okay, the C1 is on the top of y equal b. C2 is on the top of x equal a. Okay. This C1 and C2, so both C1 and C2 pass through P, okay? So we can say C1 as a function of x. Let's say g. Okay, let's imagine the C1 is a g function g, which g is defined by f x b. Okay. The same thing what we did before. So we take y as a constant b, okay, for this g. So the g prime is actually our t1. So t1 is g prime at a, or this is partial x ab. And then similarly at C2, we can define another curve, okay? Another curve, maybe function h, okay? H of y. Let's say this is going to be f, x a constant, and then y. And this is actually, if we derive, we can get the t2. So this will be h prime of b, which is the partial y of AB. So these are geometric interpretations of partial derivative that we previously see, okay, with the limit definitions. Okay. So as a conclusion, the partial x and partial y can be interpreted as the slopes of tangent line at P to trace C1 and C2 of surface S in planes y equal B and x equal A. I think let me write clearly, precise a little bit. Maybe let me rearrange this. Okay, so the partial x, partial y, actually they are slopes of the tangent line. And the tangent line is not only one, okay? In this case, when we restrict the observation for two curves, it means we have two tangent lines, okay? Okay. Okay, so for example, find slope in xy direction at half one for the function So basically what we are going to find for the slope is basically the partial x and partial y, okay? So partial x, this will be just negative x, right? And partial y is just negative 2y. So plug in x for the partial x, which is, so this is partial x at half 1 is negative 1/2. So partial y at half 1, this will be negative 2. Okay. So this means this negative half, z, or the function, so remember that z is function of xy. We can represent the function as z. So z decrease, because it's negative, 1/2 unit for every 1 unit increase in x. Okay, and this means z decrease 2 unit for every 1 unit increase in y. And then the implicit can be also applied in the partial derivative as well. To remember the implicit differentiation, then if we have like 3 variables and maybe some variable can be implicitly represent, then we can implicitly derive. Okay, I will show you in the next example. Okay, I will write the question first. So example, find So previously, we take partial derivative directly with respect to x or y. But if we are given the whole equation like this, okay, and then we have not only x, y, but also z. But the question says that the information are that z can be defined implicitly as a function of x, y. Okay. So we can write this z f x y like that. Okay. Maybe to give you some reflection what is implicit? What is implicit? This is implicit. So let me write some notes first from your Calculus 1 preview. So Cal 1 review. Recall that if we have y equal f of x, then if we have x squared plus y squared equal, let's say, or maybe minus 2x plus y, then we can take derivative and then taking 2x plus 2y dy dx minus 2 plus dy dx equals 0, and dy dx we can express like this. Okay, this is your Calculus 1. Okay, we have before we continue the last part we discussed, the implicit differentiation, let me just take example for the previous one. Okay, so suppose that we have this paraboloid like this. Okay, we have some sort of 3D structure. The function of xy is 4 minus x squared minus 2y squared. Is it correct? Oh, no, it's just y squared, sorry. This is just y squared. Okay. So just that. Okay. So let's say we have this, okay. And we would like to know the partial x and partial y at 0.11, at 0.11, which means that at partial x, we're going to fix the constant at y equal 1. Y equal 1 is a plane. Okay? If you see the 3D perspective, y equal 1 is a plane. So let me put y equal 1. Y equal 1 is there. Okay, that's the plane y equal 1. So we're going to cut this with y equal 1. And then we are going to set the some slope from this the same thing when we are going to have partial y. Partial y at 1, 1 will be cut by x equal 1. So let me take off y equal 1, and then that will be the plane x equal 1. Okay. So we are expecting the line that is cut at 1, 1, we are going to see maybe if one here, maybe it will be the slope, okay? Or maybe that. Okay? It depends on the point. Okay? So suppose that it's 1, 1, then maybe 1, 1 here, maybe it's going to be that way. Okay? So let's go back to the notes, and I will have the picture ready. And I think if you are familiar with the website, and I suggested you try this at least once. It is easy to operate. If you want to operate the 3D, you need to select the GeoGebra for the three dimension. Okay, there will be some options. You can select the 3D. Okay. If not, then the regular one is just the y-axis, and just 2 dimension. Okay. You select 3D. You can maybe, if you remember the chapter 12, the quadratic surface, you could also make the quadratic surface functions through this graph, and you can see the visuals. Okay. What will be the visuals when we have some functions? Okay. So that's the idea. So let's go back to this. Okay. So this is the so this is the plane. So the plane is quite huge, but it's cutting the sides here, and this is 1, 1. Okay, 1, 1. Or if we are taking 1, 1. Okay. So at 1, 1. So at 1, 1, we can also get the z from f11, right? We get the z. f11 is 4 minus 1 minus 1, which is 2, right? Oh, it's correct. It's 2y squared. Why I'm writing y squared? So this is 2 squared. Oh, I already correct. So it means that this is going to be 1. So the point on the surface will be 1, 1, 1. Okay. So at this point, and you see it's already cut. At this point, then this will be the C1. Okay. And another one here. This will be C2. Okay. So that's actually our partial x and partial y. Okay. So if we would like to find like partial x, partial y, then we can operate our partial derivative operations. So partial x will be negative 2x, and partial y will be negative 4y. And then we can plug in 1, right? Plug it 1, 1. This is negative 2, or just 1 is okay because it's only x or y. This will be negative 4. So you will see that here is the partial y. You see that it's, you could also think like z and y as a 2-dimension. You have linear that is decreasing, which is having this negative 4. Okay. This is for a partial x. We can see z and x. Okay. Maybe from this side, this is also decreasing. Okay. Maybe it's if you rotate this, you can see this x positive and then z is decreasing. Okay. So in partial derivative and also later in multiple integrals, there's a lot of visuals that if you're not able to imagine or to draw, it will be very difficult to make sense all the formulas. So I think using GeoGebra will be very helpful if you want to understand more on the graph and the concept. Okay. Okay, so let's back to this part. Okay, back to the implicit differentiations that we have taught before. So in calculus 1, we set y equal function of x, function of one single variable. So if we have these equations, we want to implicitly derive. We are going to set x as usual. We derive x as usual because it's it's independent variable, and then we are setting the y as a dependent of x, which means when we derive that with respect to x, we are going to include the chain rule of of y and x, which is dy dx. Okay. So every time we take y squared, we take 2y and then write dy dx, and then we take y becomes dy dx. And then we can solve this for dy dx. If the question is asking dy dx, then this will be the result, the end result. Okay. Now similarly, we are going to bring this concept into the function of two variables. Now the question is we are going to set up that the z is not. Let me write here. Maybe this is y is dependent, right? And x is independent, right? Now we take z as dependent and x, y both are independent. So depends on which one we are going to derive with. It can be partial x or partial y. For example, we start from partial x. So we are going to differentiate this with respect to x. Okay? So let me copy this, write a new one. So this will be, let's say we start from the partial x. Okay? So partial x, we state x as usual. Okay? State x as usual. 3x squared. And how about y? Remember, in partial, because we have partial x or y, when we derive with x, then x as our variable, y is a constant. Okay, so y becomes 0 in this case because a constant. So this will be 0. And z, we take z implicitly like we did in calculus 1. So we are going to write plus 3z squared and then write the z the x. Okay. And then now we have x, y, z. Remember, in this case with partial x, y is a constant. So we have x and z, which is two different functions. We can take two different functions, which means we are going to have a product rule. Okay? So xz, we can have, first is, let me write 6 and then bracket. So xz become, first one is x become 1, so it's yz, plus x, and then z become 1, but dz, we would add the dou z dou x. So it become x, y, dou z, dou x. And that's it, the procedure. And then now we can solve for dou z dou x. So we take, let me write here. Oh, I think we can cancel 3, right? We can cancel 3, all 3, and 6 become 2, right? Okay. So we can write z squared. I will move x to the right side. So let me write this, and then plus 2 xy dou z dou x. This will be negative x squared negative yz. And then we can group this. Dou z dou x is z squared plus 2xy. Let me write negative and then x squared plus yz. And then dou z dou x is negative x squared plus yz. And then z squared plus 2xy. Okay, the concept is pretty similar to what we have in calculus 1. The difference is we have, now we can have like 3 variables. One is our variable as usual. The other one is the one that we implicitly derive. And the third one becoming a constant. So let's try for partial 1. So this is partial x. We did partially derive with respect to x. Yes?
Aren't we missing the 2? The 2yz?
Oh, yeah. This one, right?
On the other side.
2xy minus 1. Oh, yeah. So this will be plus 2. This will be plus 2. Okay, thank you. Yeah, why? Okay. Okay, any questions? Okay, let's try for partial y. Okay, so this is partial for x. So take the original equations, make a copy right here. Okay. Now we take the partially derived with y. Okay, now the one that will be our independent variable will be y. X will be constant, and z is implicitly derived. Okay. So we are going to start with the 3y squared. X becomes 0, right? And then plus 3z squared and then the same thing would happen with this. So let's say this is 6, and then we have x, y, z. So the first one is y is equal to 1, so xz, and then plus z become dou z dou y, and then we write all inside. So x, y, and then equal to 0. And then similarly, we have pretty similar structure. And then your solution will be negative. Okay, becomes that. Okay. Okay, any question about the implicit differentiation? Okay. I think as long as you know the procedure, the techniques, it's supposed to be okay. Supposed to be okay. Okay, now the next one is the higher derivatives. So we consider if we have, so we have partial, we have partial x. So let me write if f is a function of two variables x and y, then we have defined the partial x as a partial derivative of f with respect x. Same way with the partial y. This is the same. So we can define, if we are taking another partial on the partial, in this case the partial x, right? This will, we can write as partial x x, okay? So this x is order, okay? It's the order. So we partially derive with x, and after that partially derive with x again, twice. And then maybe let me take this with different color to make it clear. And then if we have partial y, and then we partially with x, okay? How we write is, first we write the first one, partial y, and then x. Okay. So this is the order. So we partially derive with y, and then partially derive with x. And let's take the other ones. Take partially with y. Now we can write f x y like that. And the last one is partially y twice. Twice differentiate with respect to y. This will be partial y y, okay? Okay, suppose we have an example here, okay, just to show you one phenomenon that will be important. So we have, let's say we have f. Okay, we would like to find all of this component. So first we take partial x, taking 3y squared and plus 10x y squared, right? Now from this partial x we can derive one more with x. Y will be 0 and this x will be 1, so 10 y squared. And then we can take fxy, then we are going to derive with respect to y from the partial x. So this will be 6y plus 20xy, okay? Okay, now the second part is taking partial y. Partial y is, we're taking y and then x as constant. So this will be 6y, xy, negative 2 plus 10x squared y. And then take another derivative with y. This will be 6x plus 10x squared, okay? And then taking the partial y and then taking the x. So we are going to have 6 y, and then we have plus 20 x y. Okay, now you will see that the partial xy and partial yx, they have the same results. So we say in this case they both are getting the same results, okay. Which this get into the theorem what we call as the Clairaut theorems. Okay. So suppose f is defined on a disk and it contains a, b, and then if the functions, these two second partial derivative functions, they are continuous, then the fxy at that point equal fyx at that point. And it's not only like for two like the second derivative only. If you maybe take higher, maybe if you take the for example for three variable x, y, z, for example, you can have like f partial x, partial y, let's say partial z. Okay. The partial x, let's say x, z, z is equal partial z, x, z is equal partial z, z, x. Okay. So the way we see how these partials work is how many partial derived in the order. Okay. This is having 1x and 2z. 1x, 2z. 1x, 2z. Right? Okay. So it's also the same. Okay. Within this theorem, we can have also for other variables as well. For if we have more, then we can also do that. Like for example, if we have the here is partial x y y is equal to partial y x y equal partial y y x, and so on and so forth. And that's it, the partial derivative for at least for the techniques and procedure. Okay. I think for today, let's end up to here. Okay. Let's end up until here. So okay. So next Monday, there will be no TA class. Okay, no TA class, and perhaps your TA will give you some assignment, but I'm still not sure. And I think we don't really need any class on Monday. Okay? So you don't need to come on Monday. Wednesday we have a class, and then Thursday quiz, right? I think you prefer the Thursday quiz, right? Okay. So Thursday, not Wednesday, the quiz. Okay. And after that, we can have continue this